last chapter. Yeah. Last chapter here. We got 5 sections. So 5 sections between all of you and the end of Cal 1. So. And then some of you get to go take Cal 2, right?
I think I have to take up the linear algebra. I took my majors on chemistry because I only had to take algebra.
Yeah. Yep. That's understandable.
So my major, I have to take like 1 more math class, and I get a minor in math.
Yeah.
1 or 2 or something like that.
Yeah. For computer science.
Yeah.
Yeah.
I'm guessing that's what a lot of people do.
Yeah. I was similar because I did math and minored in computer science because we have to take some computer science too. So, yeah. Okay. So this section's a little weird because it's just a setup section. So what we're doing in this section is not really calculus yet. It's kind of motivation for how we get to the next section. Okay. So kind of like how we started out, we talked about if we were trying to find the slope of a tangent line to a curve, we did all that stuff with the secant lines and estimating what the slope of the tangent line would be based off of the secant lines. We've got a similar train of thought that we're following in this section. Okay. The big thing we're after in this chapter is to get to these things called integrals. Okay. And what integrals do for us is they help us with problems like these 2 types of problems we're going to look at. So we're starting off thinking about an area, okay? And it's not just any area. Okay? Some types of area problems we can do with elementary math, and that's not a big deal. If you think back to way back in the beginning when we were talking about our motivations for calculus, one of the problems that came up was thinking about trying to figure out the area underneath some curved shape. Okay. So the ones we're going to be looking at, okay, are set up specifically like this, where we have some curve, okay, over the x-axis, and then we're going to chop it at 2 places vertically. So our left side, we're going to call that number A, and our right side, we're going to call that number B. And then we want to find the area that's bounded by the curve on the top, by the vertical line at A and B on the left and right, and then by the x-axis on the bottom. Okay, that's where we're headed. And technically, the curve can go down below the x-axis too. We'll talk about that when we get there. Okay, but that's the idea of what we're working on here. So, some shapes, area, no big deal. You start doing some of that stuff in 4th or 5th grade, like area of rectangle. As soon as you learn how to multiply rectangle length times width, you got the area. It's not a big deal. And then we get into some slightly more complicated formulas, right? Like we can think about a triangle as like half of a rectangle. Okay, and we get our area of a triangle formula there, half times the base times the height, or half times length times the width, really what that is. And even if we have some more complicated polygon, okay, usually we can split that up into pieces and just figure out the area of each piece. So like you can take a polygon and split it into triangles, figure out the area of each triangle, and then just add all those together, and we can get the area of some weird shape, some polygon there. But the level of difficulty, or at least the level of complexity, okay, goes up when we're dealing with curves. Okay? Just like we saw how if you want a slope of a straight line, no big deal, that's 7th grade algebra. If you want a slope of a curve, that's more involved. So for trying to come up with this kind of area, 3 of the sides give us no problem, right? Straight line, straight line, straight line. So almost a rectangle. But we just got that top side that's curved there that gives us some issues. All right, so here's our kind of outline of where we're headed. Hey, we can kind of follow the same pattern we did with trying to figure out the slope of a tangent line, where we would look at the slope of a bunch of secant lines that were getting closer and closer and closer to the value that we actually wanted, and to take the limit. Okay, so we're going to look at a method that works similarly for finding this area underneath a curve. Okay, so what we're going to do is we're going to split our region that we're looking for the area for S, okay, is what we're calling it here, into some rectangles. Split it into some rectangles. So the most basic version of that, so here we've got a different curve. One's a little bit easier to start out working with. We've got the graph of x squared, so a parabola. We're looking at the area underneath the region between 0 and 1. Okay. That's almost a triangle, but we've got this curved side over here that gives us a little bit of an issue. So one pretty elementary thing we could say, if we're trying to estimate this area, the basic version of what we're going to do is we could say, all right, well, let's talk about this square, and mine's not very horizontal there, but what would the area of that square be? This side's 1, and then the height up here goes to the point 1, 1, so this side's 1. So what would the area of that square be? Yep, be 1 times 1, so the area be 1. Okay? And that does give us an estimate, because what that tells us is it tells us the area of S, okay, and we'll call it this. Okay? It's got to be between 0, because we know it's not 0, and 1, because we know that square is bigger than the blue portion. We can do better than that, though. That's not a very good estimate, just saying between 0 and 1. Okay, but at least it does give us a boundary on each side. Okay. So what we can do to improve our estimate, okay, is to use more rectangles. Okay, so there we use one rectangle, and technically it's a square because both sides, the length and the width are the same. Okay, but there we use one rectangle. If we use more rectangles, okay, we'll get a better estimate. So let's think about doing this. So we're gonna split our area into like 4 equal strips. Okay. So since the portion of the x-axis we're concerned with is between 0 and 1, that would mean this one is 1/4, and then you do another fourth to get to a half, and then 3/4, and then 1. Okay. And if we extend those strips a little bit, okay, we can turn those into rectangles. In this particular situation, what we've got going on is the upper right corner of each rectangle is on our curve that we're interested in. And there's different ways you can do that, but this one's set up that way where the upper right corner is touching. Okay. So each one of these rectangles, we know the width. Right? We've taken 0 to 1 and split it into 4 pieces, so the width of each rectangle is 1/4. And then if we wanted to figure out the height of each rectangle, what could we do? Well, we know they're this tall, and that y value is the same thing we would get when we evaluate our function at the right endpoint of that interval. So if we did 1/4 squared, because this is x squared, if we did f of 1/4, we would get the height of that rectangle. If we do f of 1/2, we'll get the height of that rectangle. If we do f of 3/4, we'll get the height of that rectangle. And then if we do f of 1, we'll get the height of that one, which we've already talked about as 1. Right. And the idea then, okay, is that we can add those areas together, and we'll get a better estimate than we got using only one rectangle. Okay. So on this one, if we do that, and we know they're all 1/4 tall, so that's where all the 1/4 in the front are coming from. I mean 1/4 wide. Okay. And then we evaluate it at the right endpoint, if you will, right corner of those rectangles. So 1/4 squared, 1/2 squared, 3/4 squared, and 1 squared. The reason why we're doing squared, don't lose track of that, is because our function here is x squared. That's where we're getting the curve from. So it's f of 1/4, f of 1/2, f of 3/4, f of 1. Okay. These parts are coming from our function. And it turns out, if you do that, we get either 15/32 as a fraction, or as a decimal, 0.46875. Okay. And if we look back, remember we're trying to get the area underneath the curve. So we're after like this area in here. Right. So if we take the area of the rectangles, the blue rectangles there, is that number going to be too big or too small? The area of our rectangles is going to be too big. Okay? It's going to be bigger than the part that we actually want. So what we can say then is that the area of our blue region, the area of our region under the curve S, has got to be smaller than what we got when we figured out the area of all those rectangles. Okay. And what's going on here with the notation, since it was the right endpoint of each rectangle that was on the graph, they're calling this thing R, and since we used 4 rectangles, they're calling it R sub 4. And that'll help kind of keep track of what's going on with the rest of this. Okay. So something else we could do though, another way we could have done the same thing, is to use different rectangles. Okay. We could use rectangles with their left endpoint touching the graph. Okay. So here we're still using 4 rectangles. It's just that this rectangle, if we're talking about it's going to be as tall as the left endpoint's at 0, so we've got a rectangle that's 0 tall on that one. But same process. Each one's 1/4 wide, and then to figure out how tall each rectangle is, we find f of the left endpoint. And so this one's 0 tall, 0 squared 0. This one we would do 1/4 squared, and this one would do 1/2 squared. What's different though, the area we get doing this, here's our number. Okay. So just the values that tell us how tall our rectangles are different. So in that one we get 7/32, so 0.2187. But looking at the picture, we said we've got this much extra when we use the right endpoints. All that's overestimate. What's going on when we use the left endpoints on the curve? We've got the opposite situation. We're missing this part, and we're missing that part, and that part, and that part that we want included. So on this one, when we use the left endpoints, the area of our rectangles, is it going to be too big or too small? Too small. Too small. So this one's an underestimate. It's too small. So we know the one on the left is too big. We know the one on the right is too small. So what that does for us is it gives us like a lower bound and an upper bound on what our area for our S region, our area under the curve, can be. We know using the rectangles that are going to give us too small of an answer, we get this. We know using rectangles that are going to give us too big of an answer, we get this. So our actual area's got to be between these two numbers somewhere. Huh? And that's just like we said, we know it's got to be between 0 and 1, but we kind of narrowed down the values by using more rectangles. And we could keep doing the same thing. So maybe we use 10 rectangles, or we use 20 rectangles, or 30 rectangles. Okay? Well, if we use the right endpoint, we're going to get an overestimate. If we use the left endpoint on the curve, we're going to get an underestimate. Okay, but when we use more rectangles, we get closer to what the actual area would be on both sides. So what we do when we use more rectangles is we narrow down the interval. Right? So we come up on the bottom number, we come down on the top number. Okay. And here's a table. Okay, that's just using more rectangles. Here's a table. Okay. So the more rectangles, the better, the more accurate we're going to be. So here, if we do 1,000 rectangles, then the ones with the left endpoints on the graph, the ones that the estimate that's going to be too small, we get this number. And the ones with the right endpoint on the graph, the one that's going to give us an area that's too big, we get this number. And that's starting to get pretty useful. So those two numbers are getting pretty close together. And in fact, when we kind of get where it seems like they're getting pretty close, we can take the average of these two, and we get a pretty good estimate of what our area is going to be. All right, so that's this number when we average this with this, find the midpoint. Okay. So looking at the pattern, right, these are getting bigger, approaching the area that we're actually looking for. These are getting smaller, approaching the area that we're actually looking for. And you can kind of see the area where they're approaching by looking at the average there. So have you got an intuition about what you think the area under that part of the curve might be? Can you tell like what pattern, with using the pattern, kind of where we're headed? Yeah, so now let's take this last significant digit off. That's really close to, it looks like we're heading toward 0.3 repeating, or 1/3. It's about 1/3. Okay. So what we could say, if we, we keep doing that, we keep making more and more rectangles. So we keep doing that thing, and then it gets labor intensive. Okay, just because we're having to add up so many areas of rectangles. Okay, but what we can say, we've done enough, we can kind of find the pattern. Okay, that we can see that the limit, as we take more and more triangles with their right endpoint on the curve, okay, or you could think about coming from the other direction, the limit, as I say triangles, as we use more and more rectangles with their left endpoint on the curve, is going to be 1/3, 0.3 repeating, 1/3. And so that limit is our area under the curve. That's what we're looking for. And the limit of those sums of rectangles, where we're limiting, thinking about the number of rectangles we're using approaching infinity. Okay, so a very large number of rectangles in there. Okay. Actually finding that limit, we get 1/3. Okay. That halfway sort of makes sense? What's going on? We use more and more rectangles, we'll get a better and better approximation. And if we think about taking the limit of how many rectangles we're using, that limit will actually give us, we think about using infinite rectangles, we actually get the area under the curve. Which in this case is 1/3, which is pretty interesting because just looking back at the picture, there's no way I would have just given that the eye test and said, yeah, okay, so under the curve, x squared between 0 and 1, yeah, that's 1/3. It's not easy to tell. Right? just so happens to come out to that nice rational number, 1/3 there. After the fact, you might be able to convince yourself. Trying to be confident on the front end is a little harder to see there. Okay, so what about our curve that's not so nice? What about this one? X squared is nice because it's just a nice, what we would say, increasing curve. And it goes up from left to right, and that's it. And we can even say it's concave up on the whole interval 0 to 1, and it's increasing on the whole interval from 0 to 1, so that's pretty nice. This thing's not as nice, okay, because part of our interval, our curve's decreasing, part of it's increasing, part of it's concave up, part of it is concave down, so not as nice. Okay. But we can do the same thing. It still works. We're introducing some new notation here for this process. So left endpoint of the whole thing's A, right endpoint of the whole thing's B. So if we use n rectangles, or n strips for right now, we're going to change them into rectangles. But if we divide it into n even pieces, that means each one's going to be B minus A, that's how long is this thing, divided by n, that's how many pieces we're cutting it into. So we're cutting it into n wide equal pieces, okay, equal strips here. We're going to have rectangles that are B minus A divided by n wide in just a second. So to shorten that, okay, we're going to call that delta x. Okay. Delta x. So delta x is how wide each rectangle is for a given n. Okay. So then each one of these little subintervals, we can give a name, right? So like we could say the first one, okay, is x0 to x1. X0 is also, we're also calling that A because that's where the whole thing starts, right? But then we just chop it into little subintervals that are all delta x wide. Okay. So that makes finding the right endpoints of each one not that bad, because we start at A, the very left endpoint, and then we just add delta x, how wide the rectangle is, and we know where that tells us where the right endpoint would be. And if we add delta x again, it gives us the right endpoint of the second rectangle. Add delta x again, it gives us the right endpoint of the third rectangle. And we can do that all the way to the end. Okay. Every time we need to move over to the next endpoint, we just add delta x, and whatever that number is. Okay. And with this notation, okay, here's what that thing would look like. Okay. So f of x1, that's just how tall our first rectangle is, times delta x, that's how wide it is. F of x2, that's how tall our second rectangle is, times delta x, which is how wide it is. We can do that for all n of these things, and we would get that sum of these rectangles where their right endpoints are on the curve. Hang in there, we're almost getting there. Okay, and same idea applies. The more rectangles we use, the better our estimate's going to be. Okay, so we get better and better as we increase the number of rectangles. Okay, so then what we can think about is we can think about the limit as n, our number of rectangles goes to infinity. Okay, and if we can come up with that limit, we can figure out the area underneath our curve. Okay. And that would work. That does work. Okay. You could do the same thing with rectangles with their left endpoint on there. Remember back with the one we actually got a number for. It didn't matter if we did rectangles with our left endpoint on the curve or the right endpoint on the curve, we got the same limit. Okay. True here. And in fact, it turns out if you investigate, so that is a nice way to do it. We either put the left endpoint or the right endpoint on the curve. Okay, and we could write our two limits like this. Okay. So got the limit of our right endpoint rectangles, and that's just this. The limit of our left endpoint rectangle, that's just that. Okay. So we're defining here the area of S, the region under our curve, under our continuous function f. That is one thing we're assuming for now, that the function that's giving us our curve is continuous. And the area under the curve is the same as that limit. We're thinking about the limit as we approach an infinite number of rectangles underneath the curve. Okay. Same thing happens if you use the left endpoint or the right endpoint. Okay. And in fact, we don't even have to be that specific. Okay. It turns out that we can use any functional value inside of our interval to give us the height of the rectangle. It doesn't even have to be the same for all the rectangles. As long as we find f of some value in the interval, use that as our height, when we take the limit, it all works out. Okay. And we can still come up with our area under our curve, even if we're not doing it the same way for every rectangle. Okay, so if we're just picking just a generic point out of each rectangle, using that as our height, then we'll write that as x star. Okay, just call it a sample point, and we can define the area that way. We don't even have to worry about it being on the left hand or the right hand side, just somewhere in the interval. Okay. Might not be super convinced on that, but it is true. It is true. So another way of writing this, is like, wait a minute, this. Okay. You can use this thing called sigma notation. Okay. So sigma notation is just a way for us to write repeated addition. Okay. Sigma just stands for sum. Okay, as a mathematical operator. So this, I'm talking about this thing. So my handwritten ones look like that. Okay. That's the uppercase Greek letter sigma. That one you've probably seen, right? Because that one you see on some fraternities and sororities and stuff. So, the uppercase ones. So that just means a sum. So what this means is we're going to add up these things, and how many of them we have are from 1 to n. So this says we're going to take f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x plus all the way till we get to f of xn times delta x. Okay. That's just another way to write that big long string of additions where we're adding up all the rectangles. So this is just the area of each rectangle, and this says add them all up. Okay. So then the way we can write our limits that we talked about, okay, so we can write them with that sigma notation. Okay. So this is this f of xi, that would be the right endpoint of each interval. It's taking that limit where we've got the rectangles with the right endpoint on the curve. This one, f of xi minus 1 would be the rectangles with their left endpoint on the curve. And then this f of x star, okay, the by, this is just where we're using whatever point out of each interval. All those are the same. and that'll give us the area under the curve. Okay. It's the area under the curve. All right. Hanging in there? Okay. Now that was a lot of conceptual, a little bit of theory thrown in there. Okay, that's the basis for what we're doing, trying to find the area under a curve. Okay. And we'll see some of this later. Okay. Now let's think about it from another perspective. Okay. Think about it from the perspective of trying to find a distance. We're not thinking about it as area underneath the curve of some function. We're thinking about it as trying to find a distance. So let's look at this. Okay. So if the velocity of some object, how fast it's going, and the direction it's going stays constant over some time period, it's real easy to get distance then. It's just velocity times how long it was traveling, we get the distance. Okay. But if our velocity changes over time, that's not so easy. So you're driving a car, and sometimes you're speeding up, sometimes you're slowing down. And then we are trying to figure out, just based on measuring your velocity at some points in time, how far did you travel? That's a harder problem. Okay. Harder problem. So let's look at an example. So we want to estimate the distance driven over a 30-second time interval, and we're supposing our odometer is broken on our car. Okay, do whatever you want to with that. Okay. We're going to take speedometer readings every 5 seconds. Okay. And we make this table so at time 0, when we start keeping track of things, we're going 17 miles an hour. After 5 seconds, we're going 21 miles an hour. After 10 seconds, we're going 24 miles an hour, and so on. Okay. So, since we're taking time in seconds, it's convenient to change our velocity to feet per second. So we're not having to deal with the miles an hour versus feet per second issue. We can convert. Okay. So if we do that conversion times 0 seconds, we're going 25 feet per second instead of miles an hour. 5 seconds, we're going 31 feet per second. Okay. So when we get our table there, it's just nice. They've got the same units. Okay. So we can get like an average, right, if we think about each time interval. So we're saying, okay, in 5 seconds, velocity is not going to vary that much. Okay. So we're driving a car. We're not like a space shuttle or anything like that. Okay. So, unless you just have a really sporty car, you're not going to change your velocity that much in 5 seconds. Okay. So what we can do, we can estimate how far we would go in that first 5 seconds. So that first 5 seconds, okay, the time between, let's go back to our table. Okay. So here we're estimating that between 0 and 5 seconds, we're going to go 25 feet per second. Okay. So if we do that, we can estimate our distance traveled, get 125 feet. So just 25 feet per second times 5 seconds in the interval, estimate we went 125 feet in that 5 seconds. Okay. And then we can do the same thing for the other time intervals. Right? So our next time interval between 5 seconds and 10 seconds, we can just say, okay, we're going to get an estimate by just assuming we stayed 31 feet per second for those 5 seconds. Okay, so 31 feet per second by 5 seconds, we get 155 feet. We can do that for each one of our time intervals. Okay. And we get an estimated distance traveled of 1,130 feet on that one. Okay. Got the idea? What's going on there? We just kind of estimate for each time interval how far we went, and then we add all those together. Because it kind of seeming similar to what we did before. Okay. Yeah, okay. So we could have done it the other way around. Okay. We could have used the velocity at the end of each interval. Okay. If we do the velocity at the end of each interval, like in our at 5 seconds we were going 31, so we could use that. Okay. And that's just like the left endpoint or right endpoint on the rectangle. Okay. If we use that method, then we get 1,210 feet traveled. Okay. So what? Same idea. If we wanted to be more accurate, what could we do? We could write down our velocity more often, get more intervals. Then for each interval, we won't have as much error. And then ideally, what would happen? We could take the limit as our time intervals approach infinity. Okay, you getting the idea there? So here's another way of writing this stuff down. So we'll say v is f of t, so a function of time. And then we're going to let t go from a to b, so our starting time and our ending time. So starting time a, ending time b. Okay. Here we do need to specify that our velocity's got to be in a positive direction every time. Okay. It starts causing an issue if we let some of our velocities be negative. So then we take our velocity reading at each time. We can split our intervals up into n equal pieces again. This time we'll just call it delta t instead of delta x. Okay. So then to get the distance traveled for each interval, it's just f of time whatever times delta t, how wide of time interval we had there. Okay. And it shakes out the same way as before. Okay. We could write all those velocities times their time intervals in sigma notation, and either using the left or right endpoint, so we get slightly different. So let's use using the left endpoint, let's using the right endpoint. But then we can take the limit. Either one we take the limit of, we'll get the same answer. And that answer is the actual distance traveled. The actual distance traveled. Okay. So two angles, two different problems that we come at, and we can use the same method to solve those two problems. Okay. And it's going to turn out that we can use the same method to solve a lot more problems other than just two. Okay. So that's where we're headed. Okay. Where we're headed with that. So this section, that's where this section stops. That's where this section stops. The problems in the assignment are setting up rectangles to estimate area under a curve, and then taking values out of a table and figuring out the estimate for distance traveled, kind of like we did in that one. So let's do an example or two, okay, where we're applying this. And then we'll be done. So here's a function. This is square root of x. Okay. So let's just be concerned with the part we can see here. So let's just be concerned with the interval of this function between 0 and 6. So what that means is we're looking for the area, okay, starting here, going to here. We want the area under the curve, so all this area in here. Okay. So one way we could estimate this area is by using rectangles with their right endpoints on the curve. Let's do it that way first. And let's keep it simple. Let's just do 6 rectangles. Okay. That way each one's 1 unit wide. Okay, so let's do 6 rectangles. So each one of these is going to be 1 unit wide. We got one that goes there, one at 2, one at 3, one at 4, one at 5, and then one way in here at 6. Okay. We want the right endpoints to be on the curve. Okay. So then to draw in our rectangles, the endpoints tell us how tall they all are. Okay. So there are 6 rectangles. Okay. So now let's figure out what that sum would be. Okay, and since we're using the right endpoints and we're using 6 rectangles, we'll call it R6. Okay. So our first rectangle is 1 unit wide. They all are. 1 unit wide. But then how tall is it? It's going to be f of our right endpoint, so f of 1 tall. Next rectangle is 1 unit wide. How tall is it going to be? F of 2, yeah, because f of our right endpoint, so f of 2. And then you can kind of get in the pattern here. Right? It'll be 1 times f of 3 tall for the next one. 1 times f of 4 tall for the next one. 1 times f of 5 tall for the next one. And our last one is 1 times f of 6. So we made it easy on ourselves. The ones don't change anything, so we can get rid of those. Just 1 times everything. So let's figure out our f values here then. So f of 1, what's it going to be? 1, yeah, square root of 1. Square root of 1 is 1. F of 2 doesn't come out nice, but it's square root of 2. So not a nice integer, but it's okay. F of 3 would be square root of 3. Yeah. F of 4 we can write down as an integer. Square root of 4 is 2. And then next one's square root of 5, and then last one's square root of 6. And it's fine if you wanted to just write square root of 1, square root of 2, square root of 3, square root of 4, square root of 5, square root of 6. So now we just want to add these up, okay, to figure out R6. So I'm bringing out a calculator. So we're just going to get a decimal approximation. We're just approximating anyway, so that's okay. So 1 plus square root of 2 plus square root of 3 plus 2 plus square root of 5 plus square root of 6. Whoa, I accidentally made a nested square root. That's not what we want. That's a whole nother class. Thank goodness. And if I can use my calculator, I'll get this in a second. Yeah, so it's like 10.832, something like that. That's 3 decimal places. Web assign will tell you how many decimal places. So. Okay. Now I got a question that goes along with that. Is that number going to be bigger or smaller than the actual area under the curve? Bigger, yeah, because we got all these pieces hanging out, right? So that's an overestimate. So we know this is too big. Okay. Now let's do it with the other rectangles. Let's do it with the left endpoint rectangles. Okay. So we'll still do 6. Keep it easy, where each one's 1y. Okay. So if we want the left endpoints to be on the curve, our first rectangle is going to be 0 tall. That is a little bit strange, but we still count it. Okay. And then our other endpoints be at these values, so this. And then this one goes here. Yeah. Okay. Same idea. Each one's 1 wide times, but this time we're using the left endpoint, so it'll be f of 0. Yeah. 0 squared, 0. That's when we get one 0 tall. And then this will be 1 times f of 1. And then 1 times f of 2. And then 1 times f of 3. 1 times f of 4. And our last one this time will be 1 times f of 5. It's really, it just flows until you got to make sure like this rectangle is left endpoints at 5. So you stop there. You don't add in another one. Okay. So what's that going to be? We can get rid of the 1s again. Okay. So f of 0, that's square root of 0, 0. F of 1, square root of 1, that's 1. F of 2, square root of 2. F of 3, square root of 3. F of 4, square root of 4, or 2, however you want to write it down. Don't mix them like I did. And the last one, yeah, square root of 5. So then what's our left rectangular sum here? Square root of 3 plus square root of 4 plus 5. So on that one, I get like 8.382. Okay. All right, so is that estimate going to be too big or too small? That one's too small because we've got, especially right here, but we've got all these pieces that we're leaving out. That's a little bit right there. So this one's going to be, well, scroll screen. This one's too small. So I know the area got to be between 8.382 and 10.832. It's got to be smaller than the number that's too big, bigger than the number that's too small. And the idea is if we increased our number of rectangles, we could keep doing that. And the limit of that process would be the actual area underneath the curve here. Let's look at WebAssign. Okay. Yeah, you're good. Oh, and for some reason, I don't know what's going on, but I can't get the assignment to show up for me to link it in Canvas. It may be a temporary glitch, but just keep in mind, just in case I can't get it to show up in Canvas, that we do have a 5.1 assignment. It's due a week from today. Not many problems because they got multiple parts. So that's basically what we just did. On one like this, we're thinking about the distance problem. We don't have to draw in the rectangles, we just got to know how to set up the sum. So, let me. Come on, man. No, hang on. Trying to just grab a. Great. Trying to just grab a screenshot here. It's just acting crazy. Let me get this in our scratch paper where we can use it. And let's just run through setting this one up real quick and then I'll let you go. Okay, wanted to put it over here, so I guess we'll do that here. Okay. So this one, if we're using the left endpoints, let's see how many intervals we got here. One, two, no, let's see. 1, 2, 3, 4, 5, 6. So got the L6 and R6 again. So L6 just means we're using the left hand endpoint, or R6 just means we're using the right hand endpoint. So each one of these time intervals, how wide are they? How many seconds? Oh yeah, 0.5. We're going from 0 to 0.5 to 1 to 1.5 to 1. Yeah, so you can, if you want to, you can just put that out front. Okay. It's like factoring the 0.5 out. Okay. And then if we're using the left endpoints, from 0 to 0.5 using our left endpoint or our left velocity, what would our velocity be? Be 0. And then on the next interval from 0.5 to 1, we use the one on the left, so it'd be 6.7. And then we can keep going, right? The next one would be 9.2, and 15.5, and 17.5. And then on our last one, between 2.5 and 3 seconds, the left-hand one is 19.4. if we're doing the right endpoint sum, each one's still 0.5. But this time on this interval from 0 to 0.5, we'll use 6.7, the one on the right side. And then for the next one, we use 9.2, the one on the right side. So then on our last one, using the one on the right side, we'll end up with our last one being 20.2. Okay. So they almost look the same when you write them down this way. Right, this one just starts one later and goes one further. Okay, so while we got it, we might as well figure out what these would be. So it's easier to put in the calculator if we got this way. So 6.7 plus 9.2 plus 15.5 plus 17.5 plus 19.4 times 0.5. This one I get 34.15. Okay. And then for the other one, 6.7 plus 9.2 plus 15.5 plus 17.5 plus 19.4 plus 20.2 times 0.5, I get 44.25. And there's my two answers. Okay. On this one, we can even figure out which one's over, which one's under. You count on all of them, say for sure. But on this one, we've got a pattern. Every next velocity is bigger than the one that came before it, so our velocity is consistently increasing. So that means that using the left endpoints will give us an underestimate, using the right endpoints will give us an overestimate. So the actual distance traveled on this one got to be between 34.15 and 44.25 feet. Okay. And we could use more time intervals. We would get a better estimate, and if we take the limit as the number of time intervals approaches infinity, we would get the actual distance traveled. That's what we're after, and when we get to it, that's what we're really after. Being able to take that limit and get the actual exact value. Okay. I think, let me scan real quick through. I think that's, yeah, same type. Same type. That one just gives you a graph instead of a table. And just estimate on there, because you can't get the exact Y value, just get as close as you can. And it'll be fine. Okay. All right, I think that's all. So I've got it set up. Hey, I know it's Friday next time. If you can help it, Friday's not a good day to miss. Okay? Friday is not a good day to miss. Friday is not a good day to miss if you can help it. It will be recorded, but.